actually, I have 11 mantras for you. I'll give you the 4 now. In everything you do, understand the root cause of analysis. Root cause has two meanings. One is called the proximate cause of failure, and second is the root cause. But what is proximate cause? Like in the case of Challenger, it was a O-ring problem. Columbia, it has a foam hitting. The second part is the root cause. Root cause was a human error. Why? Because NASA knew about the problem, they didn't do anything. So human error always is important.
This podcast is sponsored by Siemens Digital Industry Software. Learn more about their simulation and test solutions by clicking the links in the description. Build a better tomorrow faster with SimCenter. Welcome to a new episode of the Engineered Mind podcast. I'm your host Jousef, and on this podcast I'm talking to researchers, scientists and engineers and how their work is shaping the world around us. For this episode, I'm very excited to welcome Ravi Margasahayam to my show. Ravi currently serves as a foreign national tour guide and a global space ambassador for John F. Kennedy Space Center in Florida. In 2019, he was nominated by astronauts and held the position of the Solar System Ambassador for NASA Jet Propulsion Laboratory in Pasadena, California. In 2016, he officially retired from NASA after a stellar career covering over 28 plus years. He was the only person of Indian origin to work on both launch pads, Complex 39A and 39B, from where NASA sent humans to land on the moon. Ravi started his NASA career as a Vibroacoustics Researcher in 1989, followed by Chief Launch Pad Systems Engineer and System Safety Engineer on the Space Shuttle program. Later in his career, he held the highest safety and mission assurance position at NASA as the co-chair of Ground Review Safety Panel GSRP for all payloads going to the International Space Station ISS. In this podcast, we talk about how Ravi decided to become an engineer in the first place, where his fascination for engineering comes from. We cover the topics of frequency, energy, and talk about vibroacoustics. We cover T-shaped and I-shaped personality types. Ravi covers skills engineers will need to have in the future. And we will talk about how Ravi solved his hardest task and so much more. If you would like to support the podcast, make sure you give this video a like and leave a comment down below to make sure the ominous algorithm is suggesting the video to more inquisitive scientists around the world. Subscribe if you haven't already. And now, ladies and gentlemen, enjoy my podcast with Ravi Margasahayam.
Very busy. I've been traveling all over the places in India and other places, and then I came back and been hectic with writing my book. That's my main goal right now this year.
Nice.
I had to finish that for my daughter. I promised her for a long time. It's been 10 years in the making, so it's slowly happening. So hopefully it should be done soon. That's my plan.
Really cool. Is the book more for professionals or like for students?
No, it's just a very ordinary book. I didn't want to do it. I wanted even 8th graders in India and all over the world to read that, as a part of my journey from India to NASA. And more importantly, I wanted to make sure that they had hope that, someday they can reach, the same goals and ambitions, I pursued, So basically, it's a simple one. Next one I'm going to write, it will be a little bit technical about problem solving in various sectors of the economy, like railroads, mining, helicopters, commercial airplanes, and NASA. So and space, obviously, I think that would be a little bit more talking about what problems I faced in my life and how we solved it, to get the job done. Because a lot of times people give up on their jobs, and so, or in their life also they give up, and so that really bothered me quite a bit. And that's one of the reasons I wanted to make sure I write something initially just to impress upon them that NASA is possible. The second thing is the second book would be really more for engineers, because engineering is a dying art, and we got this forgetting curve every 30 years. So really, I see a big problem with many areas of engineering. So
very interesting. So that we can actually leave that in the podcast, Ravi. And with that, we'll kick it off. Ravi, thank you so much for doing this, by the way. Thanks for being on my show.
Yeah, sure. I'm glad to, and I hope people all over the world benefit from what I'm going to say and hear me out. Not that I'm the greatest, but at least we can get the job done.
Definitely. First of all, I appreciate you very much. Like when I share posts on LinkedIn and you giving us your anecdotes in the comments, sometimes I spend minutes, if not hours, reading your comments because they're so insightful. And I wish and hope that during the podcast, you will let us know more about your anecdotes. First of all, Ravi, tell the world, tell people who listen to the podcast, who are you and what's your background?
Uh, I think I've called myself an ordinary person in extraordinary space, and it's so great. I'm honored and privileged to be here with all of you. And I'm going to open up, tell my stories, good, bad, and ugly. Yes, I went as a small boy growing up in India, and my whole world was the Indian subcontinent. And then maybe 40 years later, I reached the top of my career in NASA, working 30 years for NASA and doing amazing things. My whole uh, playground was not just the Milky Way, but the entire solar system. So entire universe, I would say, because of launching the Hubble and many, many probes, the great observatories and stuff like that. So today, I serve as NASA's Global Space Ambassador. I'm also a VIP tour guide for NASA Kennedy Space Center, and I'm an international public speaker. So I serve in many capacities. Yes, I'm retired from NASA, but they still keep me engaged to do international activities to not only promote NASA, but promote space, exploration of space, mankind's um, goal to explore the new frontier of space, and also talk about STEM. So there are many, many aspects of my lecture that I hope you can learn from my mistakes and grow.
Definitely, Ravi. Before we jump into how a day of a NASA engineer looks like, can you give us a little bit of background? Why did you decide to become an engineer in the first place? Where did the motivation come from and the fascination?
Well, it's a good story. I'll try to make it short. I think my whole life was because of engineering. I started. I grew. I was born in Mumbai, but as soon as I was a few months old, my parents took me to Burma, and as a, growing up in Burma, near the border with Thailand, I saw Caterpillar tractors, and my dad was a civil engineer. So many construction equipment were hanging around my neighborhood. I was exposed to them because my dad took me to work. But more importantly, I think I came back from Kabul after Burma. My parents went to Kabul and worked for American embassy there, building airports and other things. I saw an Indian movie, Bollywood movie called Sangam, which is sort of a Pearl Harbor kind of story. Um, Two boys and a girl. In the end, the boy marries the beautiful girl. And my 10-year-old brain said, if I become a pilot, I can marry a beautiful girl and go around the world.
Mhm.
Yes, I married a beautiful girl, went around the world, 100 countries, but never became a pilot. So, like Leonardo says, if the flight was not for me, flying was not for me, let it be for others. So that pursuit of flying stuck in me, and that meant, I had to become some kind of engineer because it's all about engineering when you fly a plane.
Yeah,
Um,
what? Yeah, really
and then
cool story.
that led me to come to Mumbai and come back to Mumbai and study high school and college, but I failed in the exams in Mumbai, and
Mhm.
sort of my parents were very devastated. I was devastated, and then they moved me to Bangalore, which is now a hub of IT. That was 1970s, and that's when I got into engineering because my dad was an engineer. The school I joined in RV College of Engineering didn't even have aerospace engineering, but I said if I start engineering someday I may reach my goals of being a good engineer for myself and make somebody out of myself. And that led me to slowly to come to Germany, in fact, to work for Mercedes Benz later on after
Mhm.
I graduated in 75. And unfortunately, I didn't know German, nor I did know how to read German drawings. So that led me to Chicago. That's where I joined IIT Chicago as an aerospace engineer, and that was my start of my journey in America. Really, so I kept on pushing my dreams. I had this what they call as pit bull tenacity. I never wanted to give up my dreams of becoming an engineer, especially an aerospace engineer, something to do with flight. So, like Von Braun said, if I flight is not for me, then let the flight be for others. And that led me to Boeing and NASA. 40 years, amazing career. I never worked in India, I worked anywhere in the world. And here I come to America, halfway around the world, and I work for two best aerospace companies in the world, building helicopters, building planes, launching rockets to the entire solar system.
It's a pretty cool and fascinating story, Ravi. I'm super impressed. Where do you think the fascination of human beings and you yourself as a NASA engineer, where does the fascination of space come from? What do you think that is?
I think space was not my forte at all. Really, I was, as I said, when I grew up in Mumbai, my parents said, we don't have money to let you become a pilot, just like the movie stars. Uh,
Mhm.
uh, they said, if you fly, you die. That's what my mom said. My dad said, no money. But having as a 1 month old baby, I would fly around the world. I was traveling to Burma and Kabul, and later on, after Kabul in the 67, around 67, I was in Abu Dhabi, Dubai, Muscat. So flying was nothing new to me. I was flying in planes all the time, even as a baby, and as a kid, growing up in India, Burma, and Afghanistan, uh, and Middle East. So looking at the clouds and flying like a free bird, it fascinated me, and reading books on Leonardo da Vinci and National Geographic, reading about, the Apollo programs and things like that, really, I was just reading them. I had no fascination to space. I was just only thinking about below one carbon line. So,
Got it.
what really changed me was that Challenger accident. I would say I was working in Boeing as a aerospace engineer, having worked in railroads and mining and helicopters, commercial airplanes, and NASA in 10 years. Before I came to NASA, my previous job was Boeing helicopters in Philadelphia. And one day I was working on the Chinook helicopters, making gears and bearings, the V-22, the tilt rotor. I designed the whole gearbox. And then suddenly in the morning, there's a big explosion. And until then, really, NASA was not really sort of my cup of tea, I would say. The only time NASA came into my picture was two times in my life. One was John F. K. talked about, going to moon. The next time was 1969. The Neil Armstrongs and Buzz Aldrins, they came to visit Mumbai. The third time in 1976, right after I came to Chicago. By I came as a tourist, and I'm still here after 50 years. That's a long story. So I went to Kennedy Space Center and just toured around. It didn't mean a thing, but the Challenger accident stuck me. So you asked about engineering. So how did I enter engineering? Because of my liking for helicopters and planes. The next thing was engineering excellence. I wanted to become the best engineer in whatever I did, and that led me to Boeing. And Boeing put me in railroads, mining, helicopters. And that Challenger accident, I said, I have to be the best in engineering safety. So each level, as you see, the pyramid was going up and up. First, it was about engineering. Second, about engineering excellence. Then about engineering safety. So that led me to NASA. Really, I said, if I ever end up in NASA, I never want to uh, uh, really have any accidents. And even NASA, first time when they asked me to join NASA, I interviewed because my wife moved from Philadelphia to Florida or Orlando. And NASA said, have you launched a rocket? I said, no. Have you seen a rocket? No. I said, only rocket I knew was those tiny fireworks I was launching in Mumbai when there was this festival of lights, we call it Diwali.
Mhm.
And they were saying, how the heck I'm supposed to hire you when you don't have clue about rockets? But what I did was preparation. It's always about preparation. Luck favors a prepared mind, as they say. So I had read a book about a shuttle, so I knew all the acronyms in NASA. I knew everything about the rocket, but I hadn't seen one. But also, what I did was I told the manager. I said, look. Do you have a car? It vibrates. Do you have a plane? You sit in a plane, it vibrates. Do you have a helicopter? You sit in, that vibrates. So the rockets also vibrate. So vibration is a common denominator for all these structures. And I'm a structural engineer. So if you have a major problem on launch pad because of high acoustics, 190 decibels, so let me fix it. I know how to fix it because vibration doesn't care whether you're a rocket or a helicopter or a plane or a car, or even your human body vibrates. Every single part of your body has a natural tendency or frequency of vibration. So with that, I got my job.
Very interesting. I think Tesla even said it, right, Ravi? That we should think in terms of vibration and frequencies. Like Nikola Tesla, there's a famous quote from him saying, if we think about the world in terms of energy and frequency, then we understand the world a little bit more. So that's really, really interesting.
You're very
Would you?
true. For me, frequency, yes, matters. Resonance, we call resonance. You know what happens in resonance, right? So basically, even when a boy meets a girl, your heart starts fluttering, and that's resonance for you. So I use that analogy to really say that, everything in your body, you think your eyes don't vibrate, they do vibrate. They have a natural tendency to vibrate, but they don't have that external input like the space shuttle hitting acoustics or sound hitting. So, unfortunately, today, Jousef, many people in this world know about vibration, but very few people study vibroacoustics. And I'm the one of the
Mhm.
last Mohicans, I think, in NASA who understood 100 rockets I launched. Highest amount of decibels we launched had 190 decibels. Being born in Mumbai in the 1950s, just when Bombay talkies started, meaning there were silent movies before that, and Bombay talkies means talking sound pictures. So
Mhm.
going from a 0 dB all the way to 190 dB, that must have been an amazing journey. Just in when you start connecting things around the globe.
When you talk about vibroacoustic, what approaches did you take to actually investigate these scenarios? Did you use any special kind of NASA software that could investigate this phenomenon? How did you do that?
Well, very good point. When we started working on vibroacoustics, really, as the rockets increased in thrust, as you know, acoustic energy is directly proportional to thrust and velocity. Really, NASA didn't understand the philosophy of vibroacoustics until you brought solids into the picture. Now you know why most people in the world use liquid rocket engines. They are more benign and stuff like that. Yes, they do produce a lot of dB, but they don't have that what they call as ignition over pressure thrust. Means at T0, when you give the signal to the space shuttle, well, you would have given it the signal even earlier, like T minus 6.5, T minus 13 seconds. The pyrotechnic and the computer takes over, and T minus 6.5 seconds, the main engines come. We gimbal them, make sure 100% thrust, and then we go to solids. And these solids have to be, 1 millionth of a second. 8 bolts have to break, and the nuts have to break, and the bolts have to come down. And even if you make a tiny mistake, you're going to be a disaster. So the solids, what they do is when the exhaust comes out of the nozzle exit plane on the rocket, uh, it mixes with the ambient air, and there's tremendous amount of computational fluid dynamics won't even be doing justice to understand what kind of power and the
Mhm.
velocities we're talking about. Mach 3 exhausts and 3,000 degrees temperature, and it's amazing amount of energy and reflections on top of it. All these things, and then it swirls around and tries to go anywhere. We do put a lot of water on the launch pad to mitigate acoustics, but still, once the rocket lifts off for the launch pad, even if it goes about 1 foot above the launch pad, sound doesn't care. It goes everywhere. It goes into your payload. It goes into your crew compartment. It affects the rocket. It affects the launch pad structures. It even affects the birds and the bees around the Kennedy Space Center and the alligators. So my first job was to understand, to measure this sound energy, because you couldn't study or mitigate vibrations without computing vibrations. But to compute vibrations, you know the acoustic load. And nobody had studied that acoustic load for rockets like the space shuttle. And that's
Mhm.
where we came in. There is no models left. The first time you launch a rocket, that's your proof in the pudding, whether it goes or it doesn't go. And we have stopped the rocket one time at T minus 1.5 seconds. Can you imagine if something went wrong at T minus 1.5 seconds? You'd have a big disaster. So my first job was to understand the structures on the launch pad. They don't fly off and hit the rocket. Secondly, I had to worry about the payloads. When you have Hubble sitting in the payload compartment, or alpha magnetic spectrometer or something like that, that's a bad day for you if you blow up that payload. It doesn't matter how many launches you do in space at $500 million per shuttle launch. If the payload goes to space and doesn't work, mission is not accomplished. Mission is dead on arrival. So that is what my job was. And obviously, we don't want more than 130 decibels hitting the people, the astronauts. So my job was all this. And we kept the people around Kennedy Space Center 3 miles away. That's where we would get about 130 decibels for a short duration, which is the jet engine dB. So but the problem was there was no tools. So we had to develop the tools to go from acoustic load and put it in a vibration equation and then go from there to predict vibrations. Later on, we had finite elements. We could do PSDs and FFTs came around. When we started way back in the 60s, there was no FFTs and stuff like that. And we couldn't have all the tools with MATLAB and many, many things. Now we have finite element analysis, which I'm expert in basically. We could do that now, but not those days, And later on, even Bendat and Pearsall, who wrote the book on vibrations, they studied a lot of stuff from Kennedy Space Center. Unfortunately, my friend, who was a guy from Yugoslavia, worked for Boeing. He never wrote down anything, and so a lot of people took his details and published later on. So I tried to put a lot of publications, but obviously NASA won't let me do the theoretical work because of secret and other things. So
That's
in
really
the
interesting.
end, we did use some NASA tools. Nastran came from Cosmic Nastran, as you know. MSc Nastran was my expertise in Boeing, and then I brought it over to NASA. And we didn't use CFD. CFD was the domain of NASA Ames. So at Kennedy, we only worked on vibroacoustics. And I can challenge you. I'm one of the only persons left in the world now who knows everything about rocket noise and vibration and how to solve these problems. So
Really interesting. As you're an expert in the finite element method, and I have a ton of followers like celebrating this method, could you give us a few examples on what the FEM could be used in aerospace applications, apart from vibroacoustics?
Well, as I said, vibroacoustics is a very, very difficult phenomena to understand. Uh, even when I want to impress upon you that the first job I had, we did study in 1975 when I first went to IIT. I did use FEM, but obviously it was just very mundane things, looking at some basic structures. But once I came to helicopters division in Boeing, we had a complex problem with uh, planetary gearing. So you have a planetary, when you have power going through all the shafts and couplings and stuff like that going to the rotor shafts, you have what they call as planetary gear and a ring gear in the center, four planets around ring gear around the planets, and the sun gear in the center, and four planets running around in between the sun and the ring gear. So they are constrained at that point. But the planetary gears have bearings, and so these bearings support the load of the ring gear on one side and the sun gear on the other side. This is one of the most complex problems I ever solved. And my boss, who was Carl Albrecht, he kept on telling me that it's impossible to solve this problem on finite element analysis. So basically, we took that challenge, and one of my predecessors, who unfortunately did a lot of analysis with finite element, but in the end, he couldn't solve this problem because the test data didn't match the finite element data. Because what we did was we took the root stresses by using the strain gauge. We applied for a 34 teeth gear, we would go to every single root of the gear, put the strain gauges, and use that strain gauge data to convert stress and come up with a stress profile for the number of teeth, like 34 or 33 or whatever that may be. That profile didn't match the finite element data because the boundary conditions were wrong. And it took me first 6 months to work on that particular problem to solve it. And then in the end, I was working with a British engineer who had done a lot of helicopter work. And one day we came up with a boundary condition, and that really changed the whole uh, plan of results basically, and that really solved the problem for me. And I got a lot of awards and kudos because of that. So no, that is just one part of application. But in vibroacoustics, we did use acoustic data, and we have to predict the acoustic data on various structures. Unfortunately, as you know, on a rocket launch pad, you can't put sensors everywhere, basically, because this they will fly off. You're getting Mach 4, Mach 3 exhausts, and these will make you fly away from Orlando to California in 1 hour, by the by. So if you sit on the plume, and we couldn't predict all over the place. And this is where the problem came, because they kept on asking us, can we put a camera up close to the solid rocket boosters? And now, how do I predict the stresses on those cameras to build the structure? Because one time a camera cover flew because somebody had made a problem with the bolt nut combination, and he made a groove bigger to fit the bolt, and that camera cover blew out because of the solid rocket booster exhaust hitting it, and it took out a 10-foot section of a 1 foot thick wall, almost 10-foot sections. It took off, literally broke it, and still it kept on flying for about 500 meters. It is that kind of amount of energy we are talking about. And can you imagine just a simple foam hitting Columbia, and it created a pinhole which damaged Columbia. Now hitting these big things were a problem. So same thing happened on STS 124. So again, I got a big award, but also I have a scar on my heart, 18 scar, because I fought against the entire management for STS 125, which is the Hubble last repair mission. And on STS 124, we lost 3,500 bricks from the flame trench, which were going out at Mach 3, Mach 4 because of the solid rocket booster exhaust. And we had to come up with not only stress analysis of the walls, but stress analysis of the whole structure, as well as CFD analysis, which NASA Ames did. I didn't do it, and all these structures. So these are the kinds of examples I can give you. Not only planar structures, curvilinear structures, vibrating structures where you don't know, you can't even predict the natural frequency of vibration because the structure is so complex. And these can be solved by finite element. But just want to warn you that finite element is not the end of all means. You make a tiny mistake, 6 million parts in the space shuttle. You can blow up the rocket in a hurry. I don't care what kind of genius you are in finite element or CFD. It requires intuition, imagination, and intelligence to solve these problems on the launch pad. And you can go to any school in the world, MIT, Harvard, you name it, best schools in the world will not teach you that. It's only taught by getting your hands dirty. Uh, uh, and that's what I did, getting my hands dirty. Every time I worked, like railroads, mining, helicopters, and space shuttle. I mean, even today, you wake me up in the dream, I can tell you everything about the space shuttle. And the passion is there. That's one thing lacking in today's kids. My wife says if I cut Ravi in his hand, there's no blood coming out, only NASA comes out. And that is passion for you.
That's funny. Very, very interesting anecdote, Ravi. And that's one of my questions, actually. Do you need to be a genius to join NASA? Would have been my question, but you halfway answered it already. So you don't need to be a genius. Passion makes up for
I
it.
think you don't have to be a genius. I failed many times. The other day, I was in India trying to clean up my father's house, and I got a scorecard, mark sheet, for SSLC exam, which is the 11th grade exam in Mumbai. And this was 1968. And I sent it to my daughter, and my daughter says, Dad, is that 35 score or in a subject, or it's 85? I said, Nina, that's 35. 35 is just barely the passing grade. And Nina was laughing. My daughter Nina said, Wow, Dad, how did you end up in NASA? And now she knows, after 40 years of work, 30 years, she knows why I'm so important in NASA. So anyway, I failed in the exam in Mumbai. I didn't get good scores and ended up in Bangalore. I failed many times in Chicago. The first semester in IIT Chicago, I want to understand the English language. what the Americans are speaking, but I made it up, and now I'm the global space ambassador and public speaker for NASA. So anyway, basically, those are the failures are stepping stones. I want people to fail. It's like going through the maze, and you make a left turn, you can't go any further, make a right, and keep on doing the maze, and you learn it. So failure is a stepping stone for future successes. So don't be afraid of failure. Failure was not an option on Apollo 13. Yes, again, people forget that Apollo 13 had two parts. One was Plan A, Plan B. Plan A was to land on the moon. And you know what happened, right? So we lost the engine and we had to come back. That was a failure. But then we got the men back. So that was success. So it's a successful failure. It's not a failure in itself. So life goes through these successful failures. I want you people to read Vasa, the ship. It sunk because of its heavy weight, because of the guns in Sweden, just 1 mile away from the shore. And then now they brought it up, and now it's making more money than it ever was. Shackleton's Antarctica expedition, that's another successful failure. For me, those are the kinds of failures I went through, not only railroads and Boeing in helicopter division. All these failures were stepping stones for me. Yes, I had a failure, Columbia, and even today I cry for that. It was a stupid mistake. And that's why I fought against NASA management in 2009 for STS 125. There's a beautiful book written on that, Infinite Worlds. I want everybody to read it. I wrote the last chapter in it. And I have an 18 scar because they wanted to fire me then because I was going against the entire NASA management to shut STS 125. 1 day delay in launch cost me $1 million. Then what is the cost of blowing up a rocket? More than $10 billion or $100 billion.
Yeah, we talk about education, Ravi, which is very interesting to me. So what do you think are the skills school is not teaching students nowadays that you think are very valuable in the professional world?
Very good point you brought up. I want you to think like a T-shaped person or a I-shaped person. So I-shape, imagine you write the letter capital I. The vertical line in the middle is basically your core skills. In my case, it would be like I was a railroad engineer. I did tribology as my subject, core sciences. People forget, they do a lot of application, but they don't understand the basic fundamentals of what is friction, wear, and lubrication, what is vibroacoustics. If you don't understand the fundamentals, forget about everything. So later on, I studied mining testing and mining analysis, helicopters, how they work basically, and then planes, commercial planes, and then finally coming to NASA. I not only understood the space shuttle launches, but I also understood how payloads are designed, how rocket goes to various parts of the universe, and how we can control the 6 million parts, not having like Tacoma Narrows Bridge vibration, way back in the Seattle area. So that is the core skill you want to have. But the skills have to be supplemented, or core knowledge supplemented with basic sciences, like tribology and friction, wear, and lubrication, and vibration, and things like that. So understand that part, not just understand what is vibroacoustics and dump everything in the finite element, and it gives you garbage in, garbage out. The second part, the top part, is multidisciplinary. So I have 4 mantras, or actually I have 11 mantras for you. I'll give you the 4 now. In everything you do, understand the root cause of analysis. Root cause has two meanings. One is called the proximate cause of failure, and second is the root cause. What is proximate cause? Like in the case of Challenger, it was a O-ring problem. Columbia, it has a foam hitting. The second part is the root cause. Root cause was a human error. Why? Because NASA knew about the problem, they didn't do anything. So human error always is important. Second, multidisciplinary knowledge. Like in my case, it would be learning about railroads and mining and helicopters and commercial airplanes. So you would say, what the hell? This engineer from NASA is working on railroads. Could you imagine 10 years later when I came to NASA, every single part of the rocket launch pad on pad A and pad B, which NASA had, runs on the railroad tracks. Even the solid rocket boosters we bring from Utah comes on the railroad tracks. I was an instant expert. I learned everything in mining about instrumentation. So basically, root cause analysis of everything you do, multidisciplinary knowledge in, like in my case, helicopters, I learned about CFDs and also about finite element. And when I came to NASA, I learned about testing and vibroacoustics. That was my multidisciplinary knowledge. And then the third part is the systems engineering. People look at just the trees. When you walk on the street or the jungle, you just look at the trees. You ought to look in the eyes of the condor, fly with the eagles. Don't fly with crows and sparrows. There are a lot of them. We fly with the eagles. You get a big picture. 6 million parts. How do they work together? What happens if one part fails? And that is the beauty about understanding systems or engineering of system. Last but not least, storytelling. Storytelling, understanding what failures happen and stuff like that. So you have the core skills, then you have the multidisciplinary skills, and last but not least, which is the most important thing, the soft skills. Soft skills talk about writing basic speaking skills. I call it the max Q talks, where you stand up there and talk about 3 minutes about any subject you want and become the best in how you present to people. If you don't have the soft skills, you may have the best idea in the world. You may be a genius, Einstein, but you will never go anywhere. So I want you to be a I-shaped person or a T-shaped person or a manager, basically, and think about possibilities. We in the old days when I was growing up in India, one question, one answer, and teacher would beat me up for a second answer. In NASA, we look at possibilities, where one question has many, many possibilities. One possibility may best suit the first question, but the other possibilities will innovate you. Self innovation is more important. You innovate yourself before you innovate others, and in the end, it's all about you trying to be a all-rounder, basically. Jack of all trades, yes, it works, because a master of one is very hard to become.
Definitely. When we talk about the hardest problem you have ever solved, Ravi, could you tell us what that was and how did you approach it? Is it like the classical finite element mantra, which is divide and conquer, or how did you do it?
Uh, uh, what was the hardest problem for which area you said?
The hardest problem that you solved during your career, and how did you come up with a solution?
Okay, good call. Good, very good question. I think that the hardest problem was for us, basically. Well, there were two of them. I would say, I want to put those two in perspective, because it's all about flying. Flying, whether we are in below one Kármán line or above one Kármán line. Like the helicopter story I already told you, basically,
Mhm.
that was one of the toughest problems I worked on, understanding the root stresses of the planetary gear system. And there's a paper, actually. My boss, Raymond Rago, he went in front of the entire AGMA, American Gear Manufacturers Association, of 1,000 people lecture. He said, I screwed up the last time, and me and Ravi now solve the problem again. So this is kind of a unique, uh, uh, radical passion and obsessive focus we need to for the managers to have, saying that, hey, I was wrong. So same thing when I had my quadruple bypass. I went against the entire NASA management to look at the rocket vibration. So do you imagine that with all the NASA knowledge and engineers and the best minds in the business, including JPL, and you talk about million people around the world working for us, uh, we forgot that there is such thing as low frequency vibration coming from a 18 million pound crawler mobile launcher space shuttle transporter, which takes the shuttle from the vehicle assembly building all the way to the launch pad. It's about only a 3 mile journey. At zero point 0.8 miles per hour, you are carrying 18 million pounds on the road, and it goes all the way to the pad, and it has a 5-degree slope to go to the pad. I mean, it is one of the most complex problems. And what happened was there's back end of the shuttle. If you look at, there's three main engines there, and there's a orbiter base heat shield. What it does is when the engines lit up, the liquid rocket engines with liquid hydrogen, oxygen, the plume hits back and trying to hit the engines and the shuttle. So we put a orbiter base heat shield, and that started cracking. And this was about after 100 launches, and people were confused.
Mhm.
They had designed the rocket for more than several hundred launches each, And now within 30, 40 launches, we started getting a big problem. And then we found out that the crawler transporter, which is a behemoth, is 6 million pounds, 3 million kilos. On top of it, there's a 9 million pound mobile launcher platform, which is kept on the launch pad. It takes the load against rocket exhaust of 6.5 million pounds or 3 million kilos. This 9 million pound paperweight or 4.5 million kilos adds to the 3 million, 7.5 million already. Now we have another 1.5 million coming from the shuttle. All this weight, you would think that there is no vibration coming from a a big bearing inside the crawler, which is connected to the ground. And the ground, what it does is we have river rocks from Arkansas River and Tennessee River. So we put the rocks, and we have 456 shoes on the crawler. And each shoe, I call it the Cinderella shoe, each weighs about 1 ton. There are 456 of them, and they're using their friction, wear, and lubrication from that rocks. There is no lubricant there, just basically rubbing against the rocks. And the bearings are working hard. There's gears. All this are providing zero point zero 0.01 hertz frequency, and they're going all the way into the rocket. Can you imagine that? Nobody had realized that point 0.1, point 0.01, point 0.05 hertz frequency would go through all these rocket parts. And it took us almost a year to shut the shuttle off, study this problem, and finally we used a lot of finite element analysis, stress analysis, putting only two solid rocket boosters, putting only mobile launcher to putting on top of it. And finally we realized that this is going through the whole structure. And then we had to do there was no whole model of finite element analysis of the whole rocket. They were part of the rocket itself. Mobile launcher part was separate. The crawler was separate. There was no connectivity between those parts. It would be a humongous project. But we did it. In 2009, I got the chance, no, not 2009, a little bit before that. uh, I got a chance to present that paper in one of the conferences, and we had some Canadian partners who helped us also. So finally, we solved that problem. I think that would be one of the trickiest problems I faced. Never realizing, yes, when you have big vibration, you have big problems, but not this tiny 0.01 hertz. Going through the stack, which is 9 million kilos or 18 million pounds. And the second, the last one I think I mentioned to you, when 3,500 bricks, you can Google STS-124 problem, mission STS-124 problem. 3,000 bricks started flying. Even NASA Ames were confused, and they were telling me that the plume doesn't come around and hit the rocket. So this bricks, which are weighing about 10, 20, 30 pounds, they won't fly. And these bricks were very similar to Italian architecture when you go to Domo and some of the Brunelleschi's dome, how it was constructed. The launch pad is constructed like that because we have a concrete barrier, and on top of that we have bricks which can sustain 3,000 degrees temperature, but they are interlocking bricks. And these were the bricks which flew off since the Apollo days, 1969, we never had this problem. In 2009, we had that. In 2008, actually, when STS-124 happened, I shut the whole launch pad, and NASA wanted to fire me because I was delaying the rocket. And then finally, my management came and supported me. And later on, we did the finite element analysis, and we presented that lecture in Poland. I presented a lecture, and that was, I think, one of the finest papers I presented, because that's one thing was very tricky problem. The last but not least, there was one problem about the, if you remember ISS, it has this uh, universal connectors, basically. And this universal connectors is docking adapters. It's called IDA, International Docking Adapter. So if you have a different type of rocket by Elon Musk or by some other company, Japanese company, they will all go and mate. So it's a universal adapter, imagine, for the International Space Station. The problem was the Russians made it because they were genius in International Space Station activity before NASA. But the problem was that once the structure came to America, Boeing got the contract to refurbish it, and they put a lot of hardware and added mass and added all kinds of structural modifications and stuff like that. Guess what? It changed the natural frequency of vibration. So I kept on fighting with the NASA management and said, guys, I don't want, as a GSRP, it was my highest job in NASA as a foreigner, basically foreign born person. Ground safety review panel, which is the highest job one can get. I was the co-chair of that. So that means every single payload anywhere in the world went through me. So it may be alpha magnetic spectrometer, $5 billion, or a Japanese mice worth $500. Anyway, long story short, when NASA overruled me, Houston overruled me because they were flight safety, I was ground safety. Then I said, okay, I'm not going to sign on the papers. You can launch this, and if something goes wrong and it starts vibrating in space, you can't dock with a rocket. You may vibrate the whole space station. And space station today's cost is $250 billion. And I was instrumental in building each of the parts since Unity Node 1 and Zarya in 1998. And NASA overruled me, and I was so mad. Guess what? Maybe my prayers were okay, because what happened was it went on SpaceX 7 rocket. And as you know, what happened to SpaceX 7 rocket? It lifted off the launch pad in Cape Canaveral and blew up within a matter of few minutes. So luckily, after I told them the problem second time, they fixed it.
I see. Very interesting. So many insights, Ravi. Thank you so much. And although you said like you should get your hands dirty yourself, it would be really, really cool if you could link me to a few papers or books that people can read if they're interested in problem solving, vibroacoustics, and things like that. So I can put it in the description of the podcast. It would be really, really
Sure,
cool.
sure. Well, as I said earlier, I don't know whether people heard me or not. I've been meaning to write my memoir, my journey from India to NASA. One of the presidents
Mhm.
of India, Abdul Kalam, Dr. Abdul Kalam, he was a president of India as well as a rocket man and a missile man. When he came to NASA, I was his tour guide, and he was telling me, Dr. Ravi, I told him, I said, I'm just a humble man. I'm an ordinary person in your presence. He said, no, 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 you're also extraordinary, because when I was moving the rocket in India for Indian Space Agency, I was moving it on a bullock cart or a bicycle. So I was just like a ground person like you. But one thing you did, which I can never do it, is that you have launched 700 people to space on 100 space shuttles. And Kalpana Chawla, the first Indian woman, we got to launch her in space. And also, you're the first Indian person to work on the Indian-born person to work on NASA launch pads. So you're truly an astronaut maker of NASA. So I'm writing a book that would be more a general book about my journey, but the second book will be about problem solving on many, many fundamentals, basic sciences, which is very critical, because education doesn't provide you with all these skills. Nothing provides you.
Mhm.
No MIT, no IIT in the world can provide you, or Cambridge or whatever. I've given lectures into all these institutions, and people are dumbfounded when I start complaining about these things. Not, I wouldn't say complaining, showing them the shortcomings, about all the
You
people.
see.
So that I call, it's is the audacity of a human being to tell the truth, and truth hurts, but truth prevails.
Definitely. When you look back, Ravi, starting with your career, like more than 30 years back or 28 years plus, where do you see the skills of engineers have been, and how will the skills of engineers have to change in the future, especially with the uprise of artificial intelligence? Where do you see engineers have to become stronger at?
I think this is my opinion. Again, yes, people may not agree with me, and people will have different opinions, and they may differ from what I'm saying. But I think uh, uh, if I want all of you to read a book by Henry Petrosky. He's my sort of guru. He's a professor from Duke University. I read there's a lot of technical papers by him on the web, Google, YouTube, or even Google. But there's a book called "Success Through Failure: Paradox of Innovation" or something like that. That is very, very
Mhm.
good book. In that book, he talks about forgetting curve. So every 30 years, we go through this cycle in human uh, journey or human history. Um, you know, and I've come through two cycles, luckily. If you imagine,
Mhm.
mankind started from Africa a million years ago, Homo sapiens 60,000 years ago. Then we started going around the world. 60,000 years, we just wandered around 10,000 miles of the earth. We never went anywhere. But now in the last 60 years, you know, in my first year, I've launched probes to Ulysses to the Sun, Magellan to Venus, and Galileo to Jupiter, and Cassini to Saturn, things like that. Launched the Hubble in my first year. We built the ISS. We repaired the Hubble 5 times. What I'm trying to impress upon is, I think uh, you cannot just work in software. AI and AR and VR, they're tools basically. When I was growing up in India, my father couldn't even afford a slide rule. I used to use log tables. There were no computers then. I didn't know a word computer those days. Uh, Even when I came to America, I saw a computer in IIT far, far away. I didn't even touch a computer, feel a computer. But
Mm-hmm.
what it is, I think the human mind works when you see a picture. You identify with the picture. Same way, you have to identify the root cause of failure in everything you do, and that enforces you. That's why Petrosky says that success through failure is the only way to your great success. I've failed many times. I have literally, I've been miserable almost, up to a point where I was down all the time. So, what one must do is not rely too much on software. Yes, software is a great tool, computer is a great tool, but if you don't understand the physics of the problem, that is where you
Mm-hmm.
go wrong. As engineers, there was a nice, if I get my hands on one of the articles written by two people who are talked about safety, engineering safety. Remember, we talked about engineering safety. You know, I was a launchpad safety manager and all that. And for me, knowing every little detail on how this rocket performs, what can go wrong, how to understand each of those parts and how they fit together, and what happens at the exhaust of the rocket, how it affects the payload, all that things people forget. Nowadays engineers just okay, design this part, and they just go and design the part without understanding how it connects to the other entities. So I think my biggest challenge for the engineers today is understand the physics of the problem. And this person, who is a genius in safety, he worked for NASA 40 years, including my best friend, uh, William MacArthur the second. He was the chief of safety for entire ISS and the entire shuttle program. And my mentor has been Pamela Melroy. She's now number 2 deputy administrator of entire NASA, reports directly to Joe Biden. She was my mentor in 1996. She gave me my Silver Snoopy Award for solving a problem on the space shuttle. So now, what happened on the space shuttle? So basically, as the shuttle was coming down, suddenly the crew compartment became very, very hot. There was no coolant loop working properly. There was a water coolant loop which was going through a very quarter-inch diameter pipe. It stopped working because we were going around the world every 45 minutes. I go around the world 90 minutes. Start from Orlando, come back to Orlando 90 minutes. I see 16 sunsets and sunrise. So there is 130-degree variation, temperature variation from one side of the earth to the other side. And the water froze. Once the water froze in a small area of the pipe, which is a long pipe, and it is exposed to the payload compartment, guess what happened? There's no water coming. And these guys were very hot. And basically, to understand the water flow rate, I don't remember now. There's an article written by me, a technical memorandum for NASA. It was very, very low flow rate, and it was impossible to even measure the flow rate. And there was only one two-line calculation by NASA AIMS to tell you what the flow rate was, but never calculated. until
Mm-hmm.
until that particular time in 1995. And guess what? We took ultrasonic flow meters, and we connected these flow meters on big pipes underneath the crew compartment, where below the where the pilot and co-pilot sit, and we did everything to validate the data. We validated the data at a high flow rate, but not in flow rate. Then we had to take the sensors and send it to the factory in Boston to recalibrate them to measure very, very, very low flow rates. And then only I could measure the flow rates. And basically, for that work on the space shuttle, I got the highest award in NASA called the Silver Snoopy Award. The Snoopy dog, which is a Disney dog, is a pin made out of it. It goes to space, and Pamela Melroy, astronaut, she brings it from Houston and gives you that award. That means you are branded the best basically. And that's what I call gold standard. I want everybody who is a listener, I want to have that uh, insatiable appetite for learning, unique problem solving skills, think differently in all different dimensions, radical passion, extreme audacity, pitbull tenacity, and make sure that you are the best in the world. In the end, Jousef, your name is the only one you brought to this world, and you're not going to take only your name after you're gone. Nothing belongs to you in this world. So your name has to be gold standard. And that's help
I
people
love it.
understand the physics of the problem. If you don't understand all this software, all this hardware, computers, and best software in the world, FEM, CFDs, AI, you name it, deep learning, whatever you call it, nothing matters, because it doesn't go beyond the physics of the problem. You cannot change it. God has written down those rules.
Yeah. I see. What would you say, Ravi, during your career was the biggest technological breakthrough that was very fascinating to you? What would you say was the biggest one? Was it reusable rocket, or would you say something else that you encountered during your career?
I think there are many of them, but two things. Uh, well, I would say the next leap forward for NASA is the a laser communication, and I put a payload called Opals. You can Google it, OPALS. It's a laser communication between Earth and space, and this is the finest piece of hardware. We are going to put. If you want to travel in deep space and go deep space communications, the only way to do that is to have relays of many, many lasers, satellites, which will communicate with each other. And there was a station in California, and as the ISS was going around, we put the opals on the external part of the ISS after launching it in the space shuttle, and there would be beams communicating back and forth. And then as we came over California on the space station, I would get that data basically. And that is the future, I would say, of what we are going to be doing. And I think that is one of the finest pieces of technology. Reusable rockets, Jousef, I'm sorry to say this for you, but I used to do that with lunar modules landing on the moon and coming back. On the space shuttle,
Hmm.
135 launches. I put men in those rockets, in the space shuttle, okay, and launched them to space above one Kármán line to low Earth orbit. And they stayed there 1 month, 2 months, and then still I brought them back, landing safely where I started from Kennedy Space Center. We have the largest, longest runway in the world. Actually, cutely, we call it the alligator tanning facility because all the alligators come and tan on it, and we have to kick them out. So I think we have done the reusable part of the rocket. Big rockets, I'm not impressed with big rockets because there's a bigger thrust. So if something goes wrong, you'll blow up one engine. You can't have 33 engines like the Russians did on the N1 rocket and other things. You know what happened? One bolt came out of one of the rockets and got sucked up in the other engine. That's why Russians never went to the moon, as you know. Um, so basically, the technology is already done. The next one I would say is in my own career and on my lifetime, I was thinking about flying in 1964, as you know. In 1960, 70, I mean, not 70, 81, 82, I started working for Boeing, and I was building helicopters for a living in Philadelphia, Chinooks and the tandem rotor, V-22, the tilt rotor, the Model 360, all composite, and the Comanche helicopter. All this helicopter. Now, seeing NASA JPL, which is my own agency, flying on Mars. Can you imagine Ingenuity helicopter? So I want to impress upon you that, for me, more than Apollo 11, I would say Apollo 13 was a classic example of what human mind can do. These three men were stuck beyond the physical reach of humankind, 200,000 miles away from Earth. If you fall in a pool, Jousef, I can hold my hand and pull you out. But these three men were beyond the physical reach of humankind, but not beyond the reach of human intelligence, imagination, and ingenuity. And with those words, Gene Kranz and his whole team of people on Earth, and three men in space, two teams, fantastic NASA teams, brought them back. Why NASA is great? Because you're talking about digital twins and all that. NASA did that in 1968, 69 when we were working on the Apollo. If you Google that, you can find out about Apollo digital twins. Apollo 13, we used digital twins. Um, so basically, what I'm trying to impress upon you is that these are the kinds of technologies you want to do. You want to lead. My Voyager 1, Voyager 2 has gone beyond the solar system. Nobody will catch up with me. I met the guy who launched Voyager 1, Voyager 2, and it's amazing that kind of people I met doing the tours and stuff like that. I want your people to go around the world. You appreciate the world more. You find Henry Petrosky says, innovation starts with you first, but also you have to look around you. What is missing in this particular thing? One particular person, American, forget his name now, he went around the third world country. He saw people lifting his suitcases and then putting it on a horse cart and moving it to his hotel. He said, how come if I can combine the suitcase with the wheels, I would become a billionaire? And that's what happened. He became a billionaire. So innovation is to look at everything in this world, because everything in this world is engineered world. Like Von Karman from JPL said, scientists study the world. And we don't want all the scientists in the world because they'll never engineer a thing. Our world is an engineered world. That's why engineering is such a great profession. Science, I'm not putting down science and math. Those are quintessential to understand engineering. And technology derives from engineering. So engineering is the central part. Science and math on the other side. So scientists create the world as is. Study the world as is. Engineers create the world that never was. So it is important as a engineer to understand everything wrong with this. So innovation is just understanding the limitation of the current state of the art. If you had just a pencil without an eraser, you put an eraser in the back, something like that. So this is how innovation starts. And innovation, you can become a billionaire just by creating one tiny thing.
Very beautiful, and it makes me very proud to be an engineer, Ravi. Before I ask the last question to wrap up the podcast, I have one question for you. I'll ask that in a second, but before I do that, I would like to thank you so much for taking the time being on my show, and I'm sure there will be a second part in the future, especially when you've written your books, as you've mentioned in the beginning. So the question, to wrap this up, is how do you define success, Ravi?
How do I define success? Very, very good question. My God, you put me on the spot. Am I successful today? I don't know yet. Uh, Success for Tenzing Norgay. I met him. I was 20 years old. I was wandering the streets of Darjeeling. I went to a store and asked the guy, I said, give me some postcards of Darjeeling and Tenzing Norgay and Hillary climbing Mount Everest in 1970. This was 1973. I asked the question. But as you know, the storekeeper didn't have any pictures. Tenzing Norgay didn't know how to take a picture. And Hillary had the camera, so there's only a picture of Tenzing on the Everest. So, is Everest climbing Mount Everest on this Earth, the tallest peak in the world in this Earth, is success? I don't think so. You know why? Because it comes from horse's mouth. I asked the manager. I said, "Give me a postcard," and he said, "No, I don't have any postcard." He said, "But the guy sitting in the corner. I said, "You know who that is?" I said, "No, everybody looks the same. All the Sherpas look the same." He said, "That's Tenzing." I said, "You got to be kidding me." Then I grabbed him, we brought him outside. We had a nice chat with him, about 10 students from RV College of Engineering in Bangalore. And he said, Ravi, think, that you can't wander around the streets of Darjeeling and one day become successful in climbing Mount Everest. There's a lot of, you have to come to the base camp, but before that, there's a lot of training and other things. There's 4 base camps you have to, another camps you have to go up, and finally you reach the top. But you are born in 53. Don't even think about Mount Everest. Mount Everest has been done. It has been summited. I did that when you were born. So you find your own peak. And I'm saying, Mr. Tenzing, what the hell you're talking about? You got to be nuts. I mean, what is there to climb on the earth? So success means different things for different people. So when I started thinking about flying, maybe I thought I'll come up with the best plane in the world. Maybe it didn't happen. Maybe I thought I'll be at least a helicopter pilot or a plane pilot. Didn't happen. I said I'll be an aerospace engineer. It did happen. I said I'll work on aerospace field. It did happen, and then God forbid, nothing happened to me with all this craziness in NASA when you work right under the shuttle with toxic gases and all that. So I came to NASA. First day, first months launching probes to first year launching probes to the sun, uh, to Venus and Jupiter, and launching Hubble. I mean, is that success? I don't think so. Then we said we'll make mankind live and work well, launching the first Indian woman. Is that success? I don't think so. Then we said first person to work on the NASA launch pads. Again, it's not good enough. So we'll build the hub, International Space Station, $200 billion, module by module. Is that success? I don't think so. I think success for me is to give back to the world. Like Pamela Melroy, my mentor, said, your name has to be gold standard in the world. For that, you have to create masters and geniuses. A master is one who is not measured by the number of students he has, but by the number of masters he creates. So my goal in life is to
Nice.
give back to the world and give back to my country. Again, I don't believe in America. I don't believe in India. We are all one, basically. We are humankind. And if I help Jousef from one country or somebody else from another country, it doesn't mean a thing. For me, you are a human first. I have to respect you as a human first. I don't even care for religions. I believe in religions. I believe in God, but I don't believe in all these barriers. Even our astronauts in space, they said, Ravi, as before I say Kazakhstan, I would be in a different continent in space because I'm going at Mach 25 on the ISS. So we don't see any boundaries on Earth. So why should be there boundaries in the human mind? And that's my message to all of you. So, but one most important thing, if you want to be successful, one trait, if you forget everything I said today, it comes from Pamela Melroy and all the astronauts I launched. Self-esteem is the most important thing. Second, have no fear. Fear has two meanings: forget everything and run uphill, or face everything and rise. Take a lot of risks. By taking risks you may lose, but if you don't take risks, you'll always be a loser. So hit on self-esteem and you'll be automatically a successful person.
Love it. That was such a great podcast, Ravi. I really enjoyed being on the show with you. And hopefully there will be a second part. I'm sure the audience wants it. Thank you again so much for being on the show. And with that, we're closing the session and see you
Thank you
online.
again. Thank you, Jousef. You put my brain to work today, man. Thank you.